Hello, thank you for joining us. In today's webinar, we'll be sharing tips on developing and deploying optimization applications with AMPL. Now I'd like to introduce the first of our two presenters, Dr. Greg Glockner. Dr. Glockner is Vice President of Engineering at Gurobi Optimization. He manages Gurobi's worldwide support, has global experience in optimization training and consulting, and is winner of the Informs Transportation Science Dissertation Prize. Our second presenter today is Dr. Bob Forer. Dr. Forer is co-founder of AMPL Optimization. He's a professor of industrial engineering and management sciences at Northwestern University. He's an expert in optimization modeling systems and methods, was co-recipient of the Informs Impact Prize for development of algebraic modeling languages, and created the AMPL modeling language and system with David Gay and Brian Carringhan of Bell Laboratories.
Thank you. So I'll give a brief introduction to today's presentation. There's a lot of ways to express optimization models. Gurobi provides interfaces for popular programming languages, traditional languages like C, C++, Microsoft C# and .NET languages, Java, but also newer and other kinds of programming languages like Python, MATLAB, and R. Those are the interfaces that are included with the Gurobi Optimizer. There are also a variety of other higher-level interfaces available from open-source projects and other vendors, including spreadsheet optimizers, modeling extensions for other programming languages, and algebraic modeling systems for optimization. Today we're going to focus on AMPL. AMPL is a widely used, very popular algebraic modeling system that has some great features for fast development and great reliable deployment. So I'm going to now turn it over to Bob Forer, who will talk about AMPL in more detail.
So I'm Bob Forer, and I'm going to present this webinar on developing and deploying optimization applications with AMPL. And as Greg has said, AMPL is an example of an algebraic modeling language, but I'd like to step back just a bit and sort of say why there are modeling systems for optimization. And the way I like to think of it is there's a cycle of steps that you do in trying to develop an optimization model for any sort of application. And you start by talking to the people who have the application that you're building it for, and from that you work up a model of the optimizations that are to be performed, and then you prepare the data that's needed, often a time-consuming step, and then from the model and the data you generate an optimization problem, and you send that to the Gurobi solver, and it comes back with some solution, and then you look at the results and you report those and analyze them. Okay? And then the most important thing is you repeat all that. And you go through this cycle many times in developing a model that can actually be used practically. So the goal of a modeling system is to help you do this, to go through these steps repeatedly to the point where you have a working model. And so the goals for optimization software are do this quickly and reliably, get the results in time, so before the client loses interest in the project, and finally deploy it. I mean, use it for the purpose it was intended for. So there are many kinds of systems you could imagine doing this, and the systems I want to focus on are what I call modeling languages. Modeling languages are a popular way of addressing this need to do this cycle reliably and quickly. And they're based on this observation that the way people think of optimization problems, what I call the modeler's form, is very different from the way that the solver, like Gurobi, represents the problem, what I call the algorithm's form. And what you want to do is to think of the problem in your high-level form, where something you can really understand and work with, but at the same time you want it converted to the form that the solver is going to work with. So the idea of a modeling language is that it is a modeler's form, but it's writable in a way that it can be read by a computer system. So you write it in a form that's natural to you, and then all the work of translating it into the data structures that Gurobi needs and so forth is taken care of automatically, as is translating the results back to a form in which you can work with the results. And so the reasons to consider a modeling language are it speeds up your modeling cycles, it makes your modeling more reliable, and it makes it more maintainable. And all these things are due to the fact that you're working at a high level in a form that is natural for you to work with. And of course, I'll show an example of that in a few slides. Now, algebraic modeling languages, which are the kind of modeling language I'm going to show, are based on formulating by first representing your data in various ways and then defining decision variables. So you define the variables, those are the amounts to be shipped or cut or produced that are be defined by the optimization. And then where the algebraic part comes in is that you write a minimization or maximization function using algebra, okay? Using common algebraic notation that people are familiar with from the way mathematics is done. And then similarly, you write equations and inequalities using algebraic expressions, okay, to describe it. And as I said, I'll give an example of that very shortly. And the advantages of using an algebraic modeling language as opposed to modeling language based on some other high-level form are, first, that it's very familiar. Everybody has seen this in studying mathematics. And second, it's very powerful. All kinds of models of great complexity have been successfully written this way without too great a difficulty. And the other thing is that it's proven there are systems that have been developed to use this form and that have worked well for a long time. And so it's a form that we sort of have experience with that will work. And the algebraic modeling language in particular that I'm going to present is the AMPL language. And it's an algebraic modeling language built specially for optimization. So it's designed to describe optimization problems using algebraic expressions. And the goal is to have the expressions available in AMPL should be powerful in general, but the principles that it's based on should be natural and easy to learn. So it should somehow, if you know algebraic expressions, you should be able to use it easily. And furthermore, it should efficiently process your models and scale well with problem size, so that when you get to that big model and data set that you need to solve in real problems, it still works reasonably well. Now, the question of efficiency is something that people often ask about who are familiar with working with solvers. So I'm going to turn the floor back over to Greg for a moment to explain why you should not be too concerned with efficiency in the case of algebraic languages. Greg?
Thanks. So people ask us, what's the best language for building my optimization model? Well, a very broad question. What does it mean to be the best language? Is it the most easy to use language? Is it the language that fits best with the rest of the application, since oftentimes optimization is a part of a larger application? But oftentimes you mean what gives the best performance? Or turn it around, do you lose anything in performance if you use a high-level language like AMPL as opposed to coding directly to the solver's native interface? So let's take a look at this performance question in more detail. So let's take a look at a simple example. Here we're going to consider a simple network flow model that has approximately 100,000 nodes and 1 million edges, or think of it as 100,000 constraints and 1 million variables. Now, this is a continuous linear program. It's not an integer program, so this is a relatively easy model to solve. And we're going to consider the time required to generate the linear program and send it to Gurobi to solve, and then solve the linear program in Gurobi. So we'll break down those two times, the generation time versus the solve time. And we ran these tests as an average of 5 different trials. So all the different tests, you'll see the average results of 5 trials that were run on a fairly modern computer with a Xeon processor. So here's the code for a C program to create the variables and constraints. So this is doing this very efficiently by creating columns, one for each variable, and each variable is it's a network flow problem. The variable appears in 2 constraints. One is at the source of that arc, and one is at the destination of that arc. And so we just iterate over the number of edges in our graph, and we create the constraints. In C, for this model with 100,000 nodes and 1 million arcs, 1 million edges, it takes, on average, 0.3 seconds to generate the model. There's a little bit more code than this, but this is the main loop in our C program. Next, let's take a look at a Python code for the same thing. So now we're going to iterate over the number of nodes, and we're going to create the flow conservation constraint. So we're going to sum over the edges that come into that node and the edges that leave that node, and we're going to add a constraint that the flow in must equal the flow out, and we add that constraint to the model. This is what our sample program looks like in Python, that main loop. And not just this main loop, but the whole program, the build phase took on average 6.62 seconds. So it's slower than C. Now let's compare that with AMPL on the next slide. Here's that same flow balance constraint in AMPL. So we're going to look at every node except the source and sink of the whole graph, and we're going to have the inflow equals the outflow. We also have that sum expression like we had in Python. And this code, this one block of code, is again part of a larger AMPL model, and the total modeling time to run it takes 2.81 seconds. So let's compare these on the next slide. On the left-hand side, you see a chart showing the total run time. The solve time for these three models was the same. It was 55 seconds to solve. Now, in C, we had 0.3 seconds of model setup time. In Python, we had 6.62 seconds of model setup time. And in AMPL, we had 2.82 seconds of model setup time. So, yes, C is faster, but does it really matter? And the answer is no, because the setup time is a very small fraction of the total time, even in the worst case in Python. But even with a very easy-to-use modeling language, in this case AMPL, the setup time is a small percentage of that total run time of about 1 minute for this model. And again, this is for a linear program. If this were an integer program, not a network flow problem, but a more complicated model where it would be an integer program and there would be time spent in the branch and cut algorithm, the solve time is going to be even larger as a fraction of the total time. And so you can see even in this simple example, the setup time is still, no matter what language you're using, a very small percentage of the total time. So when we come back to that original question of what's the best language to use, you shouldn't be using the runtime as your main objective. If you're trying to pick a language, you should be basing that on the features of the language. Is that language for you easy to develop, easy to deploy the application, and also easy to maintain the application? With a modeling language like AMPL, it's extremely easy to develop, deploy, and maintain that application. In C, you saw that code just to write a simple network flow problem. It's much, much more complicated. And in fact, that was just a little snippet of the full model. The full model was much, much larger, more complicated than the AMPL code. Also, of course, how well does the language fit the needs of the application? Or what are the other tools that need to be linked in, like a database? The performance should not be your top priority. Time and memory for this model setup is, in this case, and in most cases we see, much, much less than solve time. So don't base that language selection on performance. That's the whole point of this. Bob, back to you.
So I'll go back to that slide I was on. We addressed efficient processing that scales well. And now to use the AMPL system, there are a number of contexts in which it's used. And because of that, there are a number of different ways in which AMPL gets used. And that's essentially what I want to describe for you in the remainder of this webinar. I'll start with a simple example and then build up through some of the things that you need to do in developing and deploying. So first I'll describe just AMPL interactively using a command language. You can browse the results, debug the model interactively, make the changes and rerun. This is typically what you do in development. Then I'll describe the scripting language, which essentially takes the programming that you want to do for your application and brings it into the modeling language by adding a simple programming component. And I'll describe several things that you may want to do there, which are typical of what goes on in modeling. And then finally, I'll describe the programming interface, which is the opposite. It lets you have an interfaced AMPL that's out in your programming language. So essentially, you bring the modeling language out to your programmers in developing an application. And I'll show an example of all of these. And what I want to use is one model for all of them. And what I'm going to use is a roll cutting model. It's very simple in principle, but it has many complications, and it's typical of some more complicated things that I'll discuss. And I'll first show just the solution via the command language, and then a trade-off analysis where we do some scripting. And then I'll say I'll go from the simple roll calling model to one where we actually worry about finding all the patterns for it. And I'll show some ways of doing that. And then third, I'll show one where instead of trying to enumerate all the patterns, we try to generate them by solving another subproblem. Okay? Now, in all of these, after I present each example, I'll stop for a bit and say what this is typical of in more complex, realistic applications. For a webinar, I can't give a really complex application, but I can tell you what gets more complicated in reality. So let's start with the roll cutting problem. The idea is you have these large fixed width rolls, and you need to cut them up into various widths that people have ordered. And the way you do that is by defining a bunch of cutting patterns and deciding for each pattern how many of that to cut. So here's a little diagram here. Here's a full width roll. Here are the various ordered widths, and you see off on the right here various cutting patterns. You cut one of these, and there's some waste sometimes in the pattern that's just not used. And you have to decide how many of each to cut. And the optimization model here, the decision is just how many rolls to cut according to each pattern. One set of decision variables. The objective that I'm going to start with is to minimize the number of these stock rolls that are going to be cut. Okay? And in order to satisfy the constraints, which are, of course, to meet the demand for all widths. So you have to cut enough of different patterns to meet the demands, but hopefully not more than necessary. So now let's see what an algebraic formulation looks like. That, remember, is what algebraic modeling languages are all based on. So here's the algebraic mathematical formulation. We're given a set of widths that have been ordered, and one parameter, a number of patterns to be considered. So the number of patterns that I'm considering cutting, and additional data for each width and each pattern, the number of times that width occurs in the pattern. So you can think of this as the pattern table. That defines all the patterns. It says for each pattern how many of each width are in it. And this BI here is the number of orders for each width. So together, this is algebraically describing all the data that are going to be in this problem. Okay? Now the decision variables are just the number of rolls to cut using each pattern. So they're just these xj's. Number to cut using pattern j for each j from 1 to n. The objective is just to minimize the sum of the xj's because I just want to minimize the total rolls cut. Okay? And the constraint, there's one constraint which says basically that on the left side, the number of rolls of width I cut has to be greater or equal on the right side, the number ordered. And so this summation takes the number of each pattern cut and multiplies it times the number of width I that are in that pattern. So this is an expression for the total number of width I that are cut. It has to be greater or equal to the number demanded. And that's the whole algebraic model. Now, the idea of AMPL is simply to write this exact same thing in a computer readable form. And it looks like this. And you can see there's a set. There are the 3 parameters. There's the variables. Here's the objective, sum the number cut, and here's the constraint. Okay? And I've taken the mathematical symbols and replaced them by some names that are easier to remember. But aside from that, it's the same thing. And you can see that if you compare, here's my mathematical constraint to this one, you see that there says for all I and W, well, give me this constraint for all I and widths. There's a sum from j equals 1 to n. Well, here's a j from j in 1 up to the number of patterns. And then we have the pattern matrix times the number cut is greater or equal to the number of orders. So, of course, I have to have actual multiplication sign here, but it's the same expression. And that's the whole idea of AMPL, is to use the same Same approach, just make it computer readable. Okay, so now this is what I want to give to the computer is this model and tell it to solve it. Now, of course, it can't solve this general symbolic model without some data. So I also have to give it separately from this. Notice there's no data in here at all, a data file. So here's a very simple data file. In more complicated cases, data may be read from a database somewhere or a spreadsheet or something, but here it's just in a text file, so I can put it on the slide easily. And in this case, there are 4 widths to be cut, and here's the number of each one ordered, and there are 9 patterns. There they are. And so I want to know how much of each of these patterns should I cut so that I can meet these orders and cut the fewest number. And here's my run. I say read the model and data, set the solver as Gurobi, and solve, and Gurobi quickly solves this problem. I set a couple options for display, and just say display the results. And so here's the variable, how many to cut. It says cut 13 of pattern 4, 4 of pattern 7, and 3 of pattern 9. And it takes a total of 20 raw rolls to achieve that. Now, if a modeling language just gave you the values of the variables, it wouldn't be so useful. What you really want it to do is to help you look at the solution and see what's going on. Okay? And so in AMPL, you can not display not just the values of the variables, but anything you can write down. So here's 3 examples. I asked it here to actually display that part of the pattern matrix that corresponds to the patterns that are actually used, the ones that have a variable greater than 0. Okay? And so here it prints a little table. Here I only use patterns 4, 7, and 9, and here's what they look like. Okay? In this example, I asked it to take all the widths in each pattern and add them up and tell me how much usable part of the roll was actually cut using that pattern. And so you see that the patterns vary. The pattern with the least waste is pattern 5, actually. Okay? The widths total up to 64, and the one with the most waste is this one here, 59.41. And you can see that the ones that were used, 4, 7, and 9, are pretty good. Okay, and so I can get that just by displaying this summation here. This is the sum of all the widths in the pattern, and then here I just displayed the slack and on the constraint, and this shows me that there are some overruns. So in fact, in order to get the minimum, I actually produced a few more widths than I needed for my orders here. Okay, because remember it was a greater than or equal to constraint. Now, if I'm thinking about this, it might occur to me that since these things have different amounts of waste, maybe I should be minimizing the waste instead of minimizing the number cut, because it's really the waste that I'm worried about. That's where I'm losing money. So what I can do is just go back and add another objective function. And I take this expression here, which is my expression for the amount of the roll that actually consists of widths that are cut, and I subtract that from the roll width and multiply that times another number cut, sum that up, and this is just the sum of all the waste from all the rolls that were cut. Okay? Now the one thing I have to do is I have to add the roll width as a piece of data. It turns out that the roll width is 64.5 in this case. I have to add that as my data. I keep all the other data, and now I can try minimizing either one of these 2 objectives, the waste and the number cut. Okay? And so I go back, I read the model and data in again. First I minimize the number cut, and I get what I got before. Turns out that I cut 20, and there's a waste of 63. Now I switch to the objective being the amount of waste. Okay? It turns out that the minimum amount of waste is considerably smaller. It's only 15. And when I do that, I see that the number cut in that solution is 35. Okay? And this is typical of playing with when you start working on a formulation. You try something and then you realize that you left something out. Okay? Why is it cutting 35 rolls just to get the waste down? Well, it's because it's cutting huge amounts of overruns. It's using very efficient patterns in a very inefficient way. And it does meet the demands, but it produces lots and lots of widths that you don't have any orders for. So you need to make another revision. You need to go back and set an overrun limit. And so now I've changed my cutting to say that the number of each width cut is greater or equal to the orders and less or equal to the orders plus the overrun limit. So I'm now saying, well, you're limited in how many extra ones you're allowed to cut. And now in my data, if I add an overrun limit of 6, what I see from that same example is when I minimize the number cut, I get the same as before. But now when I minimize the waste, I get the waste down from 63 to 49, okay, and I cut 21. So now I see a real trade-off. Okay, if I'm willing to cut one more roll, and I think I can do something with the slightly larger overruns, I can get my waste down somewhat. Okay? There are many other things you can imagine adding. I won't read these all off here, but I've just put those up as some examples. And that's typically what happens in model development. You go through, you look at something, you look at various values, you do a solve, you decide that something's not right, you try putting in extra constraints, variables, objectives, until it comes out as a solution you can use. Okay? And we have, besides the simple commands I've shown you, we have like a more graphical IDE where you can keep track of you can see my 2 files here and my little session over here. So that's sort of the simple introduction. Okay, and now what I want to next show is scripting, and I have a number of examples here, which I'll show at least 2 of them. What I want to do is extend the modeling language syntax now, so that besides having algebraic expressions and indexing expressions, interactive commands, I have loops and conditionals and assignments, so I can actually do something a bit more with this model than just try individual examples. And I'll show first what you could do to try to more systematically trade off the waste versus the number cut. And then I'll say something about cutting via enumeration. Now, I just put out some patterns there that I picked by just looking at it. But a more reasonable thing would be to just try to generate all the good patterns. And if you're generating all the good patterns, you may want to be able to just do that in your script. So I'll show that. And then the third thing I'll touch upon is that you might, if there are really a large number of patterns, you may want to use some kind of subproblem to generate the good patterns. So the idea is that for a subproblem, you'll solve your problem, and then you'll ask, well, what's another good pattern? How can I find another good one to add that will improve things? Okay? So let me just show the trade-offs here. What I'm going to do is I want to minimize the number of rolls cut, like I did before, and then I want to set a large overrun limit and minimize the waste, which we've seen that before. And then I want to start reducing the overrun limit one by one and seeing if the number of rolls cut begins to change. Okay? And I should see that the number of rolls cut begins to go down and the amount of waste begins to increase as I allow fewer overruns. Okay? And then when there's no further progress possible, becomes infeasible, or the number of rolls cut falls to the minimum possible, then I'm going to stop. So this is something I could do by hand, but if I'm going to have a lot of problems to look at, I would like to automate it. So here's an example of a simple script. It's on 2 slides, and there's some setup here which I won't describe, but down here you notice that I set the objective to the number cut and I solve. And now I save the results, and now I set the objective to waste, and now I'm going to do that loop. So I'm going to loop over some index starting at the big overrun limit and going down towards 0 one by one. And for each one I'm going to solve. If it's infeasible, then I break out. But if the number cut is less than the previous number, then I found another interesting solution. So again, I'm going to make a bunch of assignments to save it. And then if the number cut is equal to the minimum number from my first solve, then I'll break out. And then at the end, I print some nice results. So once I've written a little script, then I can feed in this model and it'll tell me everything about waste versus number cut. And you can see that when I just minimize the number cut, I had this much waste. But when I have an overrun of 10, the waste is much lower. And as I reduce the overrun, the waste slowly goes up and the number cut goes down until finally it becomes 20 again. And one interesting thing I learned here is that this wasn't actually the lowest waste way to cut 20 rolls. If I'm going to minimize the number of rolls, I should still be aware that given that I'm allowed overruns, there are better ways to cut 20 rolls and meet the orders. In this case, the waste is lower than it was here. So I can learn more from this script, okay? And automate that sort of thing. Now the next thing I'll show is more complicated, and that is, imagine you just want to generate all the patterns that make sense. A pattern, you could say a pattern makes sense if the amount of waste in the pattern is smaller than the smallest ordered width. So there's nothing you can do with that waste. Okay, you might want to use that pattern. So I'm just going to read as data here the demands and the raw width, and I'm going to compute the patterns and then solve. Okay, and here's the model looks pretty much the same. Okay, so here I'm just going to worry about number cut. The model looks pretty much the same, but now after the script is going to set some values up, and then it's going to do this big complicated loop. So I wrote a loop in my script to do this. Now I'm not going to try to describe this whole thing, but what I want to show is just that this thing called pattern here, this is where I'm building up the next pattern that I can use. So one by one, it builds up all the patterns I want to use. And when it gets to here, it only gets there when it's found a complete pattern. And at that point, it steps the number of patterns by one, and it copies the pattern into the pattern matrix. And it just keeps going around this until finally there's nothing more. I can now put that inside my script, and when I'm done with it, then I just solve, and I print out some results. Okay? Now when I do that, okay, I find out that actually I could have cut that using only 18 of the rows. And what's happened there is that I have 43 patterns that I found. So it turned out I only used 9 patterns before, but there are actually 43 non-dominated patterns. And these are the 4 patterns that it turns out to make sense to use. Okay? So I can now have a more powerful application. Okay? And I still haven't had to go any lower level than the modeling language. Okay? Now you might wonder, well, what about a bigger problem? So here's a much bigger and more complicated one. The widths are very close, so there are all sorts of patterns, whole lot of orders. The row width is much larger. And this one, it turns out there are 54,000 patterns. It still doesn't take Gurobi that long to solve it, and it finds a much more complicated solution. It turns out that it has to cut, over a dozen different patterns to get down to that level. And so this scales up quite nicely here. So what I want to point out here is that in a more complex setting, you typically might have a lot of data massaging that you need to do. And in many cases, a fair amount of that can be done in the modeling language using the same terminology that you used for your model. Okay? Now, a third one that I won't go through in such detail because I have a limited amount of time is you might actually want to generate the pattern list as you go along. Okay? So if there are really a lot of patterns, you might just want to solve with a subset of patterns and then add the most promising pattern to the subset by solving another subproblem. And there's a whole mathematics of this that I won't go into now. But essentially, you're solving just a one constraint problem called a knapsack problem to find another pattern that could be added. And you keep doing this as long as there are promising patterns. And then when you're done, this actually only gets you a fractional solution. And so at the end, you force everything to integer and you get using all the patterns that you've generated. Okay? And so again, you have a model. It looks the same as before. And but now you have a second model. In the second model, the variables are just how many of each width to use in the new pattern you're generating. Okay, so don't think that you need to understand why I put all this here. I'm just throwing this up to show that there's another model. Okay, and now what I want to do is show you the script, and in particular, in this script, the loop in this script has 2 solves. So it solves a cutting opt. It gets some dual values from that, and based on that, it solves a pattern generation. And if the pattern is at all useful, it adds it to the patterns. And notice that I can change my model on the fly. I can add to the number of patterns. I can put more things in the pattern matrix. And when I solve again, they're automatically there. Okay? And so by doing this inside the modeling language, I take advantage of the symbolic representation of the model and thus a high-level way of working with it. Okay? And then at the end, I solve an integer version, and all this stuff here is just to print out a nice version of the results. So when I do that, you see it generates a bunch of patterns. Okay? I actually give it some very simple patterns to start with. And then it has to have a fractional number of rows, so we see that slightly less than 18. And then if I just round all these solutions up to an integer, I get 20 rolls. But if I take those solutions and resolve it as an integer problem, it turns out I get 19. The best, remember, I could do was 18. Okay, but in this case, I didn't have to generate a huge number of patterns, and for a very complex problem, that might make a big difference. Okay, and so let me just say a bit about how this is integrated. Typically, if you're writing scripts, your system writes some files and invokes AMPL, and then AMPL runs the script. Okay? It processes everything, it invokes solvers and so forth, and writes the results at the end, and your system reads it back. And there have been implementations of this with many files, hundreds of statements. The statement counter goes up into the millions. These can be quite complex, and they've been used for many purposes. Even patterns. Patterns are actually a very valuable kind of model, and they're used not only for cutting, but for packing and for scheduling of all kinds. So that gives you an idea what the scripting is like. In the 10 minutes left, I want to say what happens if things are so complicated that you can't force them into the scripting language. Then what do you do? Because the thing is, the scripting language has some limitations. Script statements can be slow. Okay, they have to support general data set and data structures, and they're not compiled in the fast code. And the constructs are limited. The things you expect in a modern-oriented language aren't found in a simple scripting language. And they're standalone, so you have to run the script and then come back to AMPL. So we also provide application programming interfaces that let you do your data and result management in a general purpose language, and then make calls to AMPL to have it do things when you need it, and keep AMPL active while you're doing that. Okay? And so I want to revisit cutting briefly and consider a hybrid approach where the supervision is in a general language and only the model and solving is in AMPL. Okay? And I'll show an example here. And I'll use another prototyping language called MATLAB that's very popular in engineering. We have the same APIs for Java and for C++, and are working on them for other programming languages at all. And the examples are pretty much the same in any one of them. Although MATLAB being a prototyping language, they're a bit more concise. And I'll show the AMPL things in blue, the sort of AMPL objects in the MATLAB in green, and the methods that work with AMPL in purple. Okay? So the model is all blue. It's used the same sort of AMPL model as before. Okay? But now, for pattern enumeration, I'm going to load some data, and the pattern generation is right here. I wrote a different pattern enumeration function in MATLAB. And as you'll see, I'll show it to you a bit later, it's much simpler than that one I wrote in the script. And after I've done the pattern enumeration, only then do I go to AMPL. And I set up an AMPL object, read the model, and this, you'll notice there's lots of green, purple, and blue here. This page is just setting up the data in MATLAB and sending it over to AMPL. And there are many data options in the API here to help you get the data into AMPL efficiently. Okay? And then I solve, and I retrieve the solution. So I retrieve some values of some cut variables and pull them out. And now I have another function here to display the results. Okay? And what are those two functions? Well, the pattern enumeration function is extremely small, and that's because I use a recursive call. So because I can do recursive calls in MATLAB and other languages, I can make this much simpler. And with only a little bit more complication, I could speed it up as well. But even this is quite fast. And then the plotting routine is complicated, and it's more complicated than all the rest of the API routines combined while I try to get the plot to look the way I want. And once I've set this up, I can now be in the MATLAB prototyping environment. I run this on a data file for the Sorrentino example. It runs Gurobi as a result, and it pops up. They're the patterns. It says use 10 of this pattern, 4 of that one each of those, and 2 of those. And each color represents a different one of the 4 widths in the problem. So now I've built it into something bigger. And this is typical of all sorts of ways in which you want to build a modeling language model into something where there might be a lot of work to get the data ready. And you want to write that in some language environment that's appropriate for getting the data ready and before you put it into the model. And similarly, when you get the data back, it needs to be fed in to the systems that are going to use it. to get the solution into there. Here I just show a graph of it, but there are many things that are done with solutions. So this enables you, once you've developed the model in the interactive form and played with some scripts, to embed it into more of an enterprise application and still have the advantage of having the model that you can read there. So when it comes time to change it later on, you can still see what it is. Okay? And I could do the same thing for pattern generation. And in that case, where I did that little knapsack problem, I could use some library routine to do knapsack problems quickly instead of making another whole model out of it. So I have an example of that as well in MATLAB and Java, but in the interest of time, I won't present it here. So let me just say that we currently have Java, C++, and MATLAB in which you can do this pattern enumeration, and we're working on a variety of other languages. Our goal is to have APIs for all the languages that are really popular. And then you can do the same things in pattern generation as I just mentioned. Okay. So let me summarize what I've said. AMPL is useful for both prototyping and development. It has an interactive environment for getting models started and a scripting facility for working up to more complex things. And at the same time, it's set up for deployment that helps you either interacting with scripts through files or control AMPL through APIs. And let me just conclude by saying something about what this looks like in a more complicated setting. Just in the pattern generation example, in real problems involving patterns, just finding a good set of patterns, whether they're schedules of workers or patterns you can actually cut out of roles, is often much of the problem. And people spend huge amounts of time just creating good pattern generators. And so it makes sense that the pattern generator will be done in some other system, and AMPL would take care of the optimization. But what's also true is that you can never really generate, in these complicated cases, all of the great patterns. So it's not unusual that you do something where you generate a large number of patterns, and then you try solving, and then you, based on what you see in the solution, use that to guide generating some more patterns. And instead of the pattern enumeration, that's sort of the pattern generation approach. And so there's a combination of pattern generation and pattern enumeration, and typically with a series of solves for your solver. So even this simple example actually extends up to a number of quite a bit more complex things. So I hope that's given you an idea of the various things you can do with AMPL and how it can be useful for the whole cycle from prototyping through deployment. And now what I'd like to do to conclude is to tell you if you'd like to try this, how you could proceed. If you're already a Gurobi user, but not an AMPL user, then if you just contact sales at Gurobi, they'll be happy to give you an evaluation license for AMPL, so you can try it out. And we have an entire set of tutorial chapters that take you through doing all the parts of it. So really, it's quite easy to try some examples and then try something of your own. Okay. If you're an AMPL user but don't have Gurobi, then for commercial users, you can also contact sales and they'll give you an evaluation license for Gurobi. Academic users can get Gurobi just straight from the website. Finally, if you're new to both AMPL and Gurobi, then contact either one of us and we'll be happy to help you get started.